Okay, in this video I want to show how the test program can be used to calculate thermodynamic properties and thermodynamic processes associated with mixtures of gases and having those mixtures of gases being treated as either perfect gases, ideal gases, or real gases, and looking at the difference based on the assumption made as to the behavior of the gas in question. And so the first problem that we're going to do is actually the fourth problem in the homework set, OYZ, and it consists of air, which is 79% nitrogen and 21% oxygen. And for this particular problem, I'm going to show how we can put in a mixture of gases that make up something like a mixture called air. And we're going to take that air, we're going to compress it isothermally at 500 Kelvin from a 4 megapascal to 8 megapascal in a steady flow compressor at a given rate. For this particular problem, we're going to look at what happens if there is no irreversibilities associated with the process, and we want to determine what the power input to the compressor would be, and we want to look at it as either a perfect gas, as an ideal gas, or as a real gas. Again, a perfect gas is one in which we assume that the C sub P is constant, not a function of temperature. An ideal gas is one in which C sub P is a function of temperature. And finally, a real gas is a compressible gas that obeys the equations associated with real gases, and that is that there is a compressibility factor associated with the gas as it's compressed from one pressure to another pressure at a given temperature. And so this last case will be the case where we actually use compressibility charts and use the software to give us the information that we are looking for. So once again, keep in mind that there's not going to be any irreversibility associated with this particular process. And so we will then solve for the power input to the compressor and compare how each of these will have more or less work required based on how well we represent the gas. Okay, so with that, I'm going to go ahead and pull up our test software. Here we have our test software. And in this particular case, we're going to go into the test apps. And for this particular process, we are going to select it is a flowing system. And so we're going to look at it's a single flow of fluid going through the compressor. And so we're going to select the single flow process as we've done many times before. And now we're going to ask the question, what do we have in terms of the substance? And in this particular case, we're going to make up a mixture of two gases, oxygen and nitrogen. And so instead of just picking a pure gas model and selecting air, we are going to select the binary mixture, and we're going to do it one of three different ways. We're going to look at a perfect gas plus a perfect gas mixture. We'll look at an ideal gas and an ideal gas mixture, and then a real gas mixture. So the first one we're going to cover is this perfect gas. And so we select the app itself, the HTML app, and we're ready to determine a process between state 1 and state 2. Now, the first thing we have to do is we have to tell the software what is the mixture, what is what makes up this binary mixture. And in this particular case, we know that one of the fluids is nitrogen and the other fluid is oxygen. And again, we're not going to go ahead and select air, which is primarily nitrogen and oxygen, but we're going to make up our own binary mixture. And so nitrogen and oxygen. Now we have to tell the software how this gas, this mixture, is assembled. And so we have these two new inputs that we haven't seen before. The first input is the mass fraction of a substance, and the second one is the mole fraction of the particular substance. And so the way that the software works is because the mole and the mass fractions have to add up to 1, all you really have to do is assign the mass or the mole fraction to one of the components. And so you basically assign the mass or the mole fraction to the A fluid. And so we're going to go ahead and do that. And because this system, because the problem said that this was a by volume mixture, by volume is the same as saying by mole. And so we're going to now say the fraction of A in this mixture is 79%. And so upon doing that, the software knows that oxygen makes up 21%. This also will take the molecular weights, and it will then determine the mass fraction. And so this particular mixture is 79% by volume, or moles, but it's also 76.6 on a mass basis. And so because the two molecules are 28 molecular weight and 32 molecular weight, you see that the mass fraction is slightly below the mole fraction because of that imbalance in the molecular weights. Okay, so we've assigned the mixture, and so we now can put in what we know, and we know that it starts at 4 megapascal at a temperature in Kelvin of 500 Kelvin. And so with that in mind, we also know that the mass flow rate is 5 kilograms per second. And so in this particular problem, they are looking for the power input to the compressor. And so even though the thermodynamic properties will be on a mass basis, by knowing the MDOT, our device panels will give us kilowatts as a power or the work on a per time basis. And so that's our first state. And our second state then, again, we are dealing with a perfect gas mixture. And so when we go to the second state, we once again have to remind the software what the mixture is. And in this case, we can say that the mixture is YA2 is the same as YA1. We could have put in 0.79, or we could just use the variable from the previous state. And so we have our components. And again, we didn't see this before, but it actually does calculate the molecular weight of the mixture. And so as you can see, the molecular weight is between 28 and 32, and it's 28.784 because of it being 79% nitrogen, 21% oxygen. So it's going to be more heavily weighted to the nitrogen molecular weight. We know our MDOT is the same. It's a flowing system. And now we have our temperature is the same. It's a constant temperature process. And then finally, it is a compressor, and so it's going to compress it up to 8 megapascals. And so what we see in this particular two states is that the one thing that's going to change is the entropy. And so it starts off at an entropy of 6.34, and because the pressure is higher for this mixture, that implies, or that allows us to say, that the entropy is going to be a little bit smaller, because entropy is related to the disorder of the system. The higher the pressure, the more ordered the system is. And so we see that. We also, if we were interested, we can look at the flow energy, which is the J term. Now, the J term consists primarily of only enthalpy, because velocity and potential energy is equal to 0. And so we see in this particular case that J1 also equals J2, because basically the flow energy remains constant because it's only a function of temperature, and this is an isothermal system. And so now we're ready to go to our device panel to determine what must have happened, what happens as we go from state 1 to state 2. Now, keep in mind that even though it says that there's no irreversibility, that does not imply that the entropy stays the same. Okay? Entropy can change as long as there's heat transfer that is occurring to cause the entropy production to be equal to 0. And so when we go to our device panel, we then say that we are going from state 1 to state 2. Now, what do we know? Let's look at the equations, okay? To start off with, the equations, obviously going from the inlet to the exit, we see that mass flow rate is constant. We've already put that in, but we also have that m dot times the flow change, the flow energy change, is equal to, obviously, the heat transfer and the work. And this is our first law. Now, in our particular case, because temperature remained constant, this term is 0. And so what this implies is once we finally put everything in, we're going to see that the heat transfer is equal to the work. In order for there to be no temperature change, the work that was put into this system needs to be taken back out through the form of heat transfer. Now, the third equation is the most important one here, because the problem said that there was no irreversibility, which implies that S dot gen is equal to 0. Okay? So if S dot gen is equal to 0, which we're going to set, what does that mean? That means when we look at the equation here, we see that the balance on entropy, this S dot gen, is going to be equal to 0, which means that this term, since we have the m dot and we have how much the entropy in this case drops, that then has to be compensated for by a heat transfer. And so if this term is going to be positive because SI is greater than SE, this is going to be a positive influence. This has to be a negative influence to counteract that, to make it equal to 0. So that says that heat transfer is going to be taken out of the system. Now, in order for heat transfer to be taken out of the system without any irreversibility, that has to occur. If you look at the diagram here, that heat transfer in or out has to be at a temperature that corresponds to the temperature of the flowing system. And so in this particular case, we change this TB to 500. Okay, because we know that heat transfer across a finite temperature difference causes irreversibility. But so in order to not have any irreversibility, we then have to set the boundary temperature equal to the temperature of the fluid. And so by setting this boundary temperature to 500, and now we can say that there is no generation of entropy, then what we have actually done is we've solved this equation here. This term here, which it knows, this equal to 0, and TB is known, this will then calculate the value of Q dot. Actually, it's the area under the TS diagram. Now, it didn't automatically calculate it, but in the software, you have to come over to the Q dot and you kind of have to click on that button. And once you click on that button, it will actually do the calculation for you. And so once, it's kind of like an input, but all it really is this term here times TB. And that's what Q dot is with the negative sign. And then it performs the equality here on the first law, and we see that the work then is the same magnitude but in the opposite direction. And so the answer to this first problem then is that our work is 499.5, or let's call it 500 kilowatts into the compressor. And again, that's assuming that we are dealing with an ideal gas. A perfect gas. Okay, so that answers the first question. Now I'm going to go ahead, I'm going to turn off the recording, and I'm going to come back. And when I come back, I'm going to have done the problem again, assuming an ideal gas. And so I'll be right back. Okay, now I'm back. And while I was gone, what I did was I went and I selected a mixture of two ideal gases. And as you can see here, I selected the ideal gases, and so I'm now in the test app that is ideal gas model. And upon that, I then set up my two states. I have my 4 megapascals, 500 Kelvin, 5 kilograms per second. My mole fraction or my volume fraction of the nitrogen is 79. The 21 would be the oxygen. I do the same thing for state 2. State 2 goes up to 8 megapascals, same temperature, same mole fraction, same mass flow. So this is my state 2. And so what you've observed, or what you should observe, is that the two entropies pretty much stayed the same. And I'll explain that in just a second. I then went to the device panel. I said state 1 to state 2. Again, I set the boundary temperature equal to 500. I set the irreversibility, or the generation of entropy, equal to 0. I selected the Q and I got a number. I then hit continue or calculate, and I see that the work is the same amount as the work that we got before when we had a perfect gas. And so you say, well, obviously there's no difference then between those two. And the reason is because C sub P is only a function of temperature. And when you select perfect gas, it uses the C sub P associated with a perfect gas, in this case a mixture of two perfect gases, that has a temperature of 500. When you go to the ideal gas behavior, if the temperature doesn't rise, it starts with the same value of C sub P at that temperature of 500. And so the results, or the answers, are going to be the same. Now, had this been a problem where the temperature between state 1 and state 2 goes up, then there would be a difference in the final answer because of the fact that C sub P for the ideal gas would be higher than the C sub P for the perfect gas for the second state. And so those two particular conditions give you the same result. Okay, again, I'm going to now go away again, and I'm going to come back, and when I come back, I'm going to show you the results of what happens when you select real gas for the two components. Okay, now I'm back, and now this time what I've done is I have selected in the substance, I selected the real gas model. instead of perfect gas, ideal gas, I selected the third one, which was real gas, real gas. And so what you now see is a little bit different values or some other boxes. And so once again, though, I do have to specify the mixture as nitrogen, oxygen, and I did specify the nitrogen as being 79%, which means that oxygen is 21% on a volume basis. I still have an m dot equal to 5. I still have my pressure at 4 megapascals and my temperature at 500 Kelvin. Now, what has also been calculated for the pressure, it has taken the pressure and divided it by the critical pressure for this mixture. And so the critical pressure is a little bit below this 4 value. And so that makes this reduced pressure. You'll see that when I hover over this P of R1, that is designated as the reduced pressure. Our compressibility charts are plotted with respect to reduced pressure, how the pressure relates to the critical pressure. The same thing holds for the temperature. For this mixture, there is a critical temperature associated with the mixture, and now what we see is that the reduced temperature is 3.78, which means that temperature over the critical temperature is almost a quarter of this amount here. Okay, again, that seems weird, but keep in mind what we have is nitrogen and oxygen, which in order to have a dome, the dome basically is in the cryogenic temperature range. And so basically we're at a temperature of about 130 or 140 degrees Kelvin, which is the cryogenic temperature where one would see liquid nitrogen and liquid oxygen. And so it makes sense that this reduced temperature is a value that is close to 4. And so with this number here and this number here, we then could go to the compressibility charts. And the compressibility charts then would allow us to determine the compressibility for this mixture. And at this pressure and temperature, we see that the compressibility is about 1.01. And so what this says is that the compressibility of this mixture is 1% above 1. And so it's behaving pretty close to an ideal gas. It's only 1% off of being an ideal gas. And so that's our first state. Now our second state was at a higher pressure. And so when we go to a higher pressure here, we're going to see this relative pressure change. And so when I go to state 2 at 8 megapascals, now you see that the relative pressure, or excuse me, the reduced pressure is 2.14. The reduced temperature stayed the same. And so this is a different point on the compressibility chart. And this particular reduced pressure with this reduced temperature says that now the compressibility factor is about 2.5% above 1, or a compressibility factor of 1.025. And so what that tells us is that this mixture at this condition is not truly behaving as an ideal gas. There's a little bit more compressibility than what the ideal gas would say. And so this then allows us to calculate the other properties. Now, once again, let's compare what we have. We have an entropy value, and the entropy value decreased as we expected it to. But another thing that does happen is in the value of J, which is the flow energy. We see before that the flow energy at state 1 is 204, which is a function of this temperature. Well, we find that it's also possibly a function of pressure. And so we see that it's 204. And now when we go to state 2, we see that that flow energy is actually dropped some. It went from 204 to 202. It no longer is a constant because even though temperature is not changing, the pressure is changing, and the real gas behavior allows for a change in that thermodynamic property as a function not only of temperature but also of pressure. And so then when we go to our device panel, once again, state 1 to state 2, and now a little bit different thing happened now, and that is I said that the heat transfer here is to the TB of 500. Set this equal to 0, the S dot gen, and because we have the two values of entropy calculated, it then calculates this value here for the heat transfer. Now that value is a little bit different. It's 517 instead of 499. So it's a little bit higher. Why is it higher? It's higher because the entropy was also a function of temperature and pressure, and the real gas behavior said that it was different than the ideal gas or the perfect gas. And so the heat transfer is a little bit different. Now, when I say calculate, now this equation is being calculated, the first law, and now these two terms are not the same. There is a small difference. We saw that the difference was 2 parts out of 204 versus 202. And so there's a small difference here, and so now the heat transfer in this small difference gives rise to a work term that's now 508. And so the work and the heat transfer are not the same because there's a little bit of difference in the flow energy change. And so the answer now to this last part for this compressor, assuming real gas behavior, which is closer to reality, is now 508. And so it would take about a little over 1%, maybe let's see, that would be 1.6% more energy or work to compress this gas than what we would have expected it to do. So by using these compressibility charts and by using the real gas behavior, we're able to determine more closely the true thermodynamic properties associated with this particular process. Instead of using the perfect gas, which would have been a worse assumption, ideal gas about the same, but now the real gas is giving us a closer answer. And so those are then the 3 answers to this particular problem.